All right, it is 6 p.m., so we're going to get started. Welcome, everyone, and thank you for taking the time to join tonight's webinar on the importance of numerical calculations in the AP Environmental Science course, presented by leading AP Environmental Science educator and author Andy Friedland. I'm your host. My name is Thomas Mena, and I am the STEM Marketing Manager here at BFW High School Publishers. Before we begin, I would like to quickly go over some logistics as well as take a brief moment to introduce Andy. Here you will see an agenda of tonight's program. The bulk of the webinar, of course, will be Andy's presentation on the importance of numerical calculations in the AP Environmental Science course. Toward the end, however, we will also highlight, he will highlight some things about his latest third edition of his textbook, Environmental Science for the AP course. We should wrap up everything close to around 7 p.m. Eastern time. There will be Q&A openings throughout the presentation and of course at the end, and I will explain how we will work the Q&A portions in just a moment. Some other quick notes: there are many attendees, so everyone is actually muted throughout the webinar with so many people joined, which is awesome. Thank you everyone for joining. It can kind of create a little bit of chaos if we don't have everyone muted. So because of that, I will explain how we'll do the Q&A portion in a second. Also, one quick thing to note, we will be emailing a follow-up to this webinar, and it will include a recording along with some other info. So don't worry if you missed something or if you need to step away for a moment. Of course, please allow a couple days, maybe 48 hours or so, for us to send out that follow-up with the recording. And if it's been more than about 2 days, be sure to check your spam folders, as sometimes it does get sent to the spam folder. Now for the Q&A portion that I mentioned. So for questions, and this is very important during the webinar, you should see a chat function on the GoToWebinar toolbar. So in the chat function, choose the option Send Question to Staff. This way the questions will actually get sent to me and I can read them out loud for Andy to answer during the Q&A sections. And in some cases, I can actually chat the answer myself if I happen to know it. So feel free to send these questions in at, when prompted or anytime during the webinar. Again, you want to go to the chat function in the GoToWebinar toolbar, and in the chat function, you choose the option Send Question to Staff. And you can send those again throughout the whole webinar. And Andy will be at times asking for folks to ask some questions. Also, there should be a little function where you can raise your hand. Maybe you'll see that. Sometimes Andy will ask folks just to hit that to notify a yes or no on something, and I can let him know when you do that. Since there are so many attendees tonight, it is possible that we actually may not get to all the questions that you chat in. If we don't get to your question, don't worry. We will do our best to address anything that goes unanswered in our follow-up. However, feel free to send any unanswered questions directly to our marketing inbox, where myself or one of my marketing assistants can answer you directly. That email is hsmarketing@bfwpub.com. For sales related questions especially, so if you're have any kind of questions concerning price quotes, ordering information, digital options, anything like that maybe isn't a content question, although you can of course send content questions as well, feel free to contact your sales rep. If you are unsure who your sales rep is, of course, then just email hsmarketing@bfwpub.com. Your rep is definitely a resource for you and is always happy to talk to you about our books and share info, whether you're a current user or not. And even if you're not purchasing new books anytime soon, they're definitely there to help you. So again, we will show this email later on at the end of the webinar, but just remember you can always reach out to us there if we don't get to your question, or if you think of one after the webinar. So now it's my pleasure to introduce our esteemed presenter, who many of you in the AP Environmental Science community, I'm sure, are already very familiar with, Andy Friedland. Frankly, one slide cannot do justice to the amount of accomplishments and credentials Andy possesses. I could have filled many slides with all the great things Andy currently does and has done. Along with being the co-author of the leading AP Environmental Science textbook program, which again I mentioned is now in the 3rd edition, Andy was actually the founding chair on the AP test committee for AP Environmental Science, and he is a current professor and chair of the Environmental Science Studies program at Dartmouth. I personally am awed by his dedication to not only environmental science and its betterment, but also to education itself. So without further ado, I would like to say thank you, Andy, for your time and attention tonight presenting to us, and I will pass the screen to you so we can get started.
Thank you, Tommy. Give me a second here as I figure out how to take control of the screen. Let's see. There we go.
Yep, I see your screen.
Excellent, great. So can I just ask, can everyone who is on right now, can you hear us okay? Could you hear Tommy okay? And can you hear me okay right now? Tommy, does anybody, oh, and please raise your hand if you found that button. Please let us know. Are you seeing some hands going up, Tommy?
I am seeing many hands going up, so I think we are good.
Excellent, great. Okay, well, welcome everybody. You heard what this is about and what we're doing. So I'd like to show you that for my aspect of this talk, and together we'll keep this to under 60 minutes, we hope. I want to present practical methods for introducing and explaining numerical literacy and problem solving in environmental science, and that's in large font because that's what I think I will spend the most time on. But then I also want to describe the newly revised 3rd edition of our book towards the end. So that's what we're going to do. As Tommy mentioned, I was the chair of the committee that created AP Environmental Science, and that meant designing the course, working out the proportions of time spent on different subjects, and I helped develop the first few exam offerings. I came back 10 years later and was a member of the first assessment committee, which reevaluated AP Environmental Science. And since roughly 2009, I have no official or unofficial involvement with AP Environmental Science or the College Board. So I am now just talking as someone who teaches environmental science at the college level, and I do visit some AP institutes over the summers and talk to teachers and present information. And in fact, some of the slides I'm presenting today have been presented at some of the AP institutes over the past few summers. So a previous chief reader of the APES exam stated around 2010, maybe it was a little earlier, that fluency with numerical manipulation was essential to success on the APES exam. And I always have told people, and I like to do this with my own college undergraduates, is find stories your students care about. Maybe they're ripped from the headlines of newspapers and websites, or maybe they come from data from their daily lives. But I encourage my students to manipulate data, to do calculations, to come to answers or perhaps tentative conclusions about environmental science. And I want to give some examples of doing that tonight. But here's a more recent comment. This came from the College Board totalregistration.net, which I bet some of you monitor. The author wrote, "Nice work. This year's AP Environmental Science students achieved the highest percentage of exams scoring 3+ in this subject this decade." So I imagine some of the teachers listening today were some of the teachers responsible for that. So congratulations and thank you. The comment went on to say that students scored well on multiple choice questions about population and land and water use, but struggled on questions about global change, and that in the free response areas, students generally scored best on the ocean acidification, which was question number 3, and scored worst on the 2 questions that require scientific calculations. So I've been saying that comment in the previous slide. Fluency with numerical manipulation was essential for over a decade, but here it is reaffirmed this year. So what I want to do is talk about that and talk about how you can introduce that to your class or make that a higher proportion, a larger component of your class, which will not only ensure success or hopefully encourage greater success on the AP exam for your students. But I think it also makes people a more aware citizen and a more intelligent questioner of things that they see around them in the natural world. So here's an example. Almost every textbook, whether you're using our book or another book, or you don't use a textbook, every environmental science course at some point shows trophic pyramids. And a classic example that we use in our book is the Serengeti ecosystem. And you've got producers like grasses and primary consumers like zebras and secondary consumers like lions. And you could just ask a question on your own. What is the energy transfer in percent from producers to primary consumers? So you can see in this that producers are 10,000 joules and primary consumers are 1,000 joules. And so the transfer of energy is 1,000 joules over the original number, 10,000 joules, and that gives you 0.10. And then to obtain percentage, you multiply by 100, and the answer is 10%. So Tommy, could I ask you if the pointer is showing up?
Yes, I can see the pointer, and yep, I see you were highlighting the amount there.
Okay, so like if because I don't see it, so 10% is getting highlighted?
You just highlighted this there, yep.
Okay, great, thanks. Sorry for that interruption. So that's a simple example that you, or sorry, did you say something else?
No, I said you're all good, sorry.
Okay, so that would be an example of what you could do without any help from anybody else. But in our book, we do the math, and in this case, you have an example of how you could actually calculate or compare population growth in two countries. So this is a do the math box that in our third edition is on page 242, and something similar to it is in our previous, or certainly in our second edition. And in this case, it says Hungary and Sweden are two countries. They each have 10 million people, and they have different birth rates, crude birth rates and crude death rates, and they ask you to go ahead and calculate that, or they ask your students to go ahead and calculate that. And before I go any further, I'll just point out that in the previous pages in our textbook, we are showing that the crude birth rate is roughly, CBR is the number of births per 1,000 individuals in the population per year. The crude death rate, CDR, is the number of deaths per 1,000 individuals per year, and the growth rate in percent is the crude birth rate minus the crude death rate divided by 10. And you divide by 10 because both the crude birth rate and the crude death rate are per mil. That is, they're per 1,000 individuals. So in order to bring it to a percentage per 100, you divide the difference from crude birth rate minus crude death rate by 10. The other thing you need to know to do this do the math box is the doubling time, which is 70 divided by the percentage growth rate. And I'm sure some of you have derived this or seen more explanation on it. But very quickly, here's an example in our do the math box, which occurs towards the end of this module in our textbook. We learn that Hungary, and in a lot of cases, going these over with your students time and time again allows them to read a word problem and understand what they need to pull out. So the text tells you Hungary has a crude birth rate of 10 and a crude death rate of 13. So plugging that into the formula, it tells you that you should be going 10 minus 13, and then we know the formula takes the difference of that and divides it by 10. So in this case, we get 10 minus 13 divided by 10, or minus 0.3. So the growth rate is minus 0.3. This is a little bit of a trick question because when you calculate the doubling time, you get a negative number. And so not only do your students need to get experience with solving a mathematical problem, but then ask, what does this mean? So the time for this population to double is minus 233 years. That means it's never going to double. So the question of how many years or when will this population double in the country of Hungary, the answer is never. And this could lead you to lots of discussions about what does it mean when countries are experiencing negative growth, and are there any other countries that you know about, and how about the United States? Without immigration, what would our growth rate be like? And so there's a lot of discussions you can have that takes a calculation and branches it out or broadens it to something that might occur on, say, a free response question. And then real quickly, just to look at Sweden, a country that, again, you have to go to the top and read that there is a crude birth rate of 12 and a crude death rate of 9. It's a positive 3. So you get 70 divided by 0.3 equals plus 233 years. So this is saying that Sweden will double in size in 233 years. Then we have a your turn, where in our book we give a similar question, maybe different in some ways, and ask students to calculate it. You have the answers and they don't have the answers, so those are useful to do as an exercise. So here's the material that one might have extracted from the pages prior to that Do the Math box. But what I'd like to spend the bulk of the time on is more involved problem solving. And this is an example that I made up based on interests of some of my undergraduate students, which maybe they are interested in automobiles or they're interested in home electricity use. And so I asked my students to do things like calculate for their families how much electricity does their house use in a year, or maybe they get that from an electric bill, or estimate how much fuel, if they own a car or somebody in their family owns a car, how much fuel do they use? And inevitably that will lead to, like, which contains more energy? A car that uses 400, or not the car, but the 400 gallons of gasoline that a car uses in a year, or the electricity that in the northeastern United States a home might use in 1 year. A typical home might use 8,000 kilowatt hours. I know that in some places you might use a little bit more than that if there's air conditioning and things like that. Did you notice I just put in a kilowatt hyphen hours? So first establish that they are both quantities of energy. A quantity of fuel has a certain energy content, and then you have a gallon of gasoline. You can identify what that energy content is. And same with a kilowatt hour. It's not a kilowatt per hour, it's a kilowatt hour, which generated by a variety of sources has a certain energy content. How do I get the 400 gallons? Well, there used to be that an average car in the United States drove 10,000 miles per year, and an average car might have gotten 25 miles per gallon. I made this problem up a few years ago before we could use calculators in APES exams, so I just made them relatively easy numbers to do. In all honesty, it might be more like 12,000 miles per year, and maybe 30 miles per gallon is a typical car. But at any rate, when you divide 10,000 miles per year by 25 miles per gallon, the miles cancel out, and you get 400 gallons per year. Note that the efficiency of a car, 25 miles per gallon, is maybe the published efficiency, and some of you have probably used onboard computers on some cars that tell you how much is calculated as the miles per gallon for the car as you operate it. And my experience is those are always very optimistic and usually a few miles per gallon higher than if you fill the tank and determine the miles driven on the odometer since the last time you filled the tank, and oftentimes you then get something closer to a true number for the fuel efficiency or mileage rating for your car. But at any rate, let's say we have 400 gallons of gasoline that we used, and we look up or we provide for our students that a gallon of gasoline contains 132 megajoules of energy content. So a mega is a million, or 10 to the 6. So 132 megajoules is the quantity of energy within a gallon of gasoline. And I want to point out that an energy constant such as this would be provided on an APES exam. A student would never be asked to have memorized something like the conversion from gallons of gasoline to megajoules of energy content within that gallon of gasoline. But an arithmetic equation, 400 gallons of gasoline times 132 megajoules per gallon, the gallons cancel out and you're left with megajoules, and you get an answer of 52,800 megajoules of energy content. Now, I know some of you are already saying, but wait a minute, there was some energy that needed to be input to produce the gasoline, to extract it from the ground and refine it. And maybe that's around 15%. But let's just hold that for a minute. And you're absolutely right if you're saying, no, that's not the true energy input to the car, but it's a pretty close approximation. But doing electricity is a little more complicated. Again, this is a typical northeastern home, 8,000 kilowatt hours per year, and there are homes, say, in the southeastern United States or southern United States where air conditioning is used, and you might see a lot more usage. Maybe an average home is 12 or 14,000 kilowatt hours per year. What is a kilowatt hour? So 1,000 watts used for 1 hour is a kilowatt hour. What's a watt? A watt is a joule per second. And so a watt has a time component in it. I find that my students are always asking when I say that hairdryer uses about 1,000 watts. They go, is that 1,000 watts per hour or what? And no, a watt is an instantaneous measure that is representing joules per second. So a kilowatt hour has 3.6 megajoules of energy content. And I need to put a plug in over here I imagine a lot of you do use kilowatt meters. Tommy, do you mind asking how many people have used a kilowatt meter in one or more of their courses or for themselves? And in a few seconds, if you don't mind giving me an update, please do. But a kilowatt meter is a great thing that you can buy for around $20 or $25. Many libraries lend them out. And it allows you to plug it into the wall and plug an appliance that goes on and off like a refrigerator. Even though it's plugged in, it goes on and off during the day and night, and learn how many kilowatt hours it uses in a day. And then you can multiply that by 365 to figure out how much it uses in a year.
Yeah, actually about a dozen people raised their hand, and I guess, to say that they have used kilowatts. And Billy let us know he actually has a classroom set of kilowatts. So definitely.
Excellent. Okay. So that's great to know. Thanks. What I do like to say, and this is true, maybe it's more true for undergraduates than for high school students, but with anybody, you are dealing with electricity, and you hope that they're not going to take it home and plug their mom or dad's arc welder into this thing, but actually it only does 110 volts. But, you do have to exercise some caution if you're setting students loose with these things, but they are a great way to determine the amount of electricity usage, particularly for something that cycles on and off, like a refrigerator or a dehumidifier. But they do have a wattage rating of, I think, around 15 amps, so you do have to be careful of that. Sorry for that aside, but what it lets you do is say that if you know you have 8,000 kilowatt hours per year, you take that 8,000 kilowatt hours and you multiply by 3.6 megajoules of energy content per kilowatt hour of electricity. And when you do that, you get 28,800 megajoules. Now, you may be tempted, but I bet you're not, to say, wait a minute, 52.8, so the car uses more energy in a year than a house? And that is not totally true. So let's summarize. But first of all, I want to say it again, an energy constant such as this would be provided on the exam. No student would be asked to memorize that the energy content of a kilowatt hour of electricity is 3.6 megajoules. But the summary of what we've done, our work, our calculation so far, is that a year of car travel with our example of a car uses 52,800 megajoules, and a year of household electricity usage is 28,800 megajoules. But we are not done, and all students and teachers of environmental science know that there's embodied energy in electricity. And so maybe sure, Tommy, you're about to say something?
Yeah, I was going to ask, sorry to break you up there. I did have one question that came in about kilowatt meters. Sean let us know that he has a class set of meters, but he wanted to ask if kilowatt meters are still useful for calculating phantom loads.
Oh, great question. Is a kilowatt meter useful for calculating a phantom load? My experience with phantom loads So, okay, to define it, also people call it vampire loads. A phantom load is a load that an appliance or device demands, so it's electricity or wattage that it's demanding when the user thinks that it's off. So we often turn things off, like instant-on televisions or sound systems that might draw a small amount of electricity even when they're, quote, off. Another example is we think our chargers for our cell phones and laptops are off when we unplug the device, but they're still connected to the wall. And so the answer is, if you plug in anything that has a box on the plug, like an iPhone charger or other kinds of chargers, if they're at all warm to the touch, that means that they are demanding a phantom load. And my experience with kilowatt meters is they only measure instantaneously 1 watt. So most of these loads on like a cell phone charger that's plugged in or a laptop charger that's plugged in is milliwatts. It's tens or hundreds of milliwatts, but it's much smaller than a watt. So when you plug it in, it looks like the instantaneous reading is 0 watts. But if you put it in the mode of kilowatt hours and you leave it plugged in for like a day or a week or even a month, you might notice that after a month, and I've done this, it might use a kilowatt hour. And I can't remember if it was a number of weeks or it was a month or more. But so that's maybe a longer answer than you wanted. But you can use them for phantom loads. But my experience is most phantom loads are less than a watt. And so you really have to let it run for a long time to it add up to where it clicks from 0 to 1 kilowatt hour. I hope that answers the question.
I think it did. Sean, if it didn't, just chat in the box there. Also, Andy, some folks are looking at the math on the screen, and they were wondering, this actually doesn't have to do with the content, if there's any way we could shrink the notes portion of the PowerPoint so the slide appears a little bit bigger so they could see the numbers.
I'm so sorry. Yeah, of course. I have nothing in my notes, but I didn't. Oh, it's a good thing. I didn't realize if I had something in my notes, you'd all be reading it. But there's nothing in the notes. So thanks for that. Is this better?
Yeah, I think that's much better. And but that said, I haven't seen anything from Sean, so I think your answer about
Sean's happy. Okay, and I was expecting somebody to correct my math or told me that I didn't cancel my units correctly, and that's also, I want to take the opportunity to make the point, and I bet all of you do this with your students, but it's really important to include all units in the answer, and I hope I've done that in all of my examples. I know we have in our book because we've had like a dozen people proofread and edit them, but my PowerPoint slides, they're just me, and I work on them, and so I hopefully haven't missed any, but please let Tommy know through chat if you find a mistake, or send me an email afterwards. I'll give you my email address on the last slide. So at any rate, the summary of what we've done so far is to say that a year of car travel requires 52,800 megajoules of gasoline. A year of electricity usage in a household is 28,800 megajoules, but we're not done. You can't leave it there. When you're an environmental scientist and you're thinking about systems, you have to ask the question, which required more energy to get it to the car or to the household? And in this case, I already mentioned that gasoline, perhaps it's 15% higher if you talk about the embodied energy to extract petroleum, produce petroleum and refine it to gasoline. A typical number that people like to use is 15%. But in terms of electricity usage, you need to know how that electricity was generated. And so it's almost a trick question and a good one to ask your students. Say, okay, is this the answer? Right here, a car uses more energy in a year than this typical household that we came up with. And absolutely, even though the math might suggest the car uses more, in the more complex systems analysis of environmental science, you have to say it depends. It depends on how that electricity was generated. And if it was generated from the grid in the United States, then the answer is absolutely no, you're not done, and no, the car does not use more. So a rule of thumb is that if you generate your electricity with natural gas, it might take double the energy content of natural gas to get this much electricity. And rule of thumb is that if you generate your electricity with coal, then it might be 3 times this quantity to get that much electricity. So let's explore this. And I like this example because it shows you how maybe you can ask a numerical question and then have a broader synthetic equivalent to a free response question with different things going on. So roughly speaking, coal conversion to electricity is about 33 to 36% efficient. And natural gas conversion to electricity is about 50%. It might be a little bit more than that, but these are what allowed me to use the 3x and the 2x that I showed you in the previous slide. But this allows someone to take an example. This is a picture from our book where we looked at, and this is in figure 5.6 on page 52, where we gave a systems diagram, showed the efficiency from coal at the power plant all the way to a light bulb in the house. And this is perhaps a more detailed assessment than we need to do for the problem we've just been doing. But this example shows that if you're using coal, about 35% or roughly 1/3 of the energy contained in the coal is converted to electricity. About 2/3 is lost as waste heat and noise and particulates and carbon dioxide and other pollutants. This diagram shows you, and we're not going to go into it here, but there are transmission line losses, and then there's the efficiency of the actual appliance. And efficiencies are multiplicative. So you take this 0.35 and you then multiply it by 0.05, or sorry, you multiply it by 0.9 and then by 0.05, and the overall efficiency from the power plant to an incandescent light bulb is a pretty low number. And I don't generally get too depressed about things, but this is a, I don't know, pretty depressing situation to see this kind of a number. So I don't know if I dare do this, but I'm going to try to go to, is this better for people? Tommy asked for a show of hands, because what I did is I just made it full screen, which I hadn't done.
Could you click a couple times? Right now I'm just seeing a blank screen.
Okay.
So, I don't know, you might have animations.
All right, I'm going to go back to here. I presume you can see this.
Yeah, this we can see. I think if you just keep the notes minimized, you know, we still see the slide pretty well enough.
Okay, great. So the question is, how does this household get its electricity? And if it were coal, the energy in the coal might only release 1/3 of that as electricity. So the amount we needed in our house, we actually probably would have to generate 3 times, we'd have to use 3 times that energy content in coal to obtain this much electricity. That's the point of this slide. And you may be saying, but wait a minute, what if your house is powered by solar or wind? And that's true, depending on the time of day. And here's a nice diagram from Tesla showing that if you were going directly from some photovoltaic panels to your house, and it was during the day and you weren't relying on any kind of storage, you might say that, yes, in that case, your house does need that much electricity, and a car requires more energy to power it for a year. So to summarize, our typical car uses 52,800 megajoules per year, and a little bit more for the embodied energy to produce gasoline. Our typical household uses 28,800 megajoules per year in electricity, and that might have required twice the energy content if from natural gas, 3 times the energy content if generated by coal, and if it was generated by solar panels in the backyard and your usage coincided with electricity generation, or you had batteries which have a charge and discharge efficiency, so it's not exactly 100%, but it might be a lot closer to that 28,800 megajoules. So that is an example that I made up using things that are of interest or become of interest to my students, because I asked them, how much does your family use in a year for gasoline? Or what does the electric bill look like for your house? Go ahead and ask your mom, your dad, your sibling, whoever takes care of electricity bills for you. So that is something, and I think that's a good point to stop for a minute and see if Tommy, if you've gotten any questions or anything I misstated or didn't state clearly enough or whatever.
I will, no questions in right now, but again, everyone, if you go to the chat function in the GoToWebinar toolbar and then just type your question in there, and then you'll see a to section, just say, send it to that to questions, send questions to staff. Sorry, couldn't get that out. So it should say send questions to staff. And some of you are, sending in a couple questions earlier that I've answered some non-content questions. But right now, no questions about this current slide deck at this moment. So I'll maybe give it 10 more seconds here, and then if none come in, we could keep going. So.
Okay, well, excellent. I don't necessarily interpret that to mean I gave a flawless presentation without errors. It could just be you're being shy or you want to check yourself before you ask the question. And so as Tommy said, please ask the questions later, if not now, and that would be fine. What I'm going to do is show you another example that I made up just in the last few weeks because of new data that came from the car manufacturer Nissan. And I'm not going to go through this. It's 2 slides, and I will let you look at it. But I learned from a Nissan ad about the Nissan Leaf Plus that is, to my knowledge, just released. And it's kind of pricey, but nowhere near as pricey as a Tesla, and it's an all-electric car, and there are all kinds of tax incentives. And typically with Nissan Leaf, a year or two later, you can buy them for like half or a third of the price. So this is perhaps a little bit more like a real world other than a Tesla. And they let me know that there was a 64 kilowatt hour battery and it travels 225 miles on a full charge. So if you have students in your class who are car geeks, and everybody has some males or females in the class who are totally into cars, maybe you could ask them, how much does it cost to operate a Nissan Leaf per mile? And I worked out that calculation. So the cost to drive is maybe 4 cents per mile for a Nissan Leaf. And then I went back to the previous example, the internal combustion car that got 25 miles per gallon. And in my part of the country right now, gasoline is selling for $2.50, and I'm getting about 10 cents a mile. So I'm getting that a gasoline car, just to pay for the fuel, is 10 cents for a mile, and an electric car is 4.2 cents. Of course, there are lots of other things, and a great question to ask your students, if you were to ask them to make this calculation, is what else do we have to think about? And I came up with environmental costs and purchase costs. So I came up with a lot of things we could talk about, and the first one is what we've already alluded to, but it gives you an opportunity to talk about, well, how did we generate that electricity? And if it's a thermal electric generation process like coal or oil or natural gas, you need to talk about a boiler and steam and a turbine and a generator. And I like to tell people that if they understand how this coal-burning power plant works, you understand a lot of other power plants, such as natural gas or nuclear, or even if you just take this turbine in the center of this figure 34.7 and stick that turbine way up in the air, you've got a wind farm, you've got a wind generator. And you can basically say that once you understand this diagram, you know how a wind turbine works. Take this same turbine and put it under water, and you can understand how hydroelectric generation works, and even maybe tidal generation. So there's a lot you can do with a diagram like this, and the previous problem might introduce this section. You can also go qualitatively, and this is our figure 34.5, and it's using coal as an example, but it could also use another fuel like petroleum or anything else, and it talks qualitatively about all the different features or all the different processes, and the red arrows indicate where energy is being lost. So those are some things that you can talk about. Another thing you can talk about, and I'm a big fan of the Energy Information Agency at the Department of Energy, which, unlike every other country in the world, we use quadrillion BTUs, which are 10 to the 15th British thermal units. So you do have to explain that in order to use the data from the US Department of Energy, but it allows you to get a snapshot of what is the picture, what is the energy picture in the United States. So this shows, for example, that for all energy uses, we use petroleum and then natural gas. Those are our two largest providers of energy, and then coal and nuclear and renewables is 11%. And this one breaks out for 2018, and you can get new data as soon as it becomes available. The 2018 data just came available earlier in the summer. This is what you can see. So I'm a big fan of starting with something like a discussion about a Nissan Leaf or a Tesla Model 3, and then rolling over to what do we use our energy, how do we get energy in this country, and then there are other diagrams that show what we use it for, like transportation or industry and so on. The other thing that's more direct to a Nissan Leaf discussion is how do we get electricity in this country? So our fuel mix for electricity generation in the United States in 2016, and I don't have newer numbers, I wasn't able to find them. If you find them on the EIA website, please let me know. But I found that our fuel mix was for electricity across the United States, 34% natural gas, 30% coal, 20% nuclear, and you can see the smaller amounts. And this varies by region. So you may be well aware that if you're in the Midwest, you might be 60 or 70% coal. In fact, in the Northeast where I am in New England, I live in Vermont, I work in New Hampshire, coal is down at like 10%, and we have a slightly greater amount of natural gas, we have a slightly greater amount of nuclear fuel, and we have a slightly greater hydroelectric. If you're listening or watching from the Pacific Northwest, you might be up at 20, 30, 40, 50% hydroelectric. So this is a great diagram to show for the country and ask your students to hunt around and try to find the fuel mix. And I use search terms like fuel mix, electricity generation, and the name of a state. Because I have students from all 50 states and elsewhere in the world who do projects for me in my undergraduate courses where we hunt this down, the fuel mix for where they live. I want to also point out that there are other diagrams which let you see the primary energy consumption by major fuel source over time. This is showing from 1950 to 2018. And if you hover over the diagram at a certain point, it pops up and shows you things. This would let your students, for example, to get graph reading skills if you wanted to use a diagram like this, and then they can check their fuel mix for any given year by hovering over that year, and you'll get a readout of what the breakdown is of coal, natural gas, and so on. Ultimately, everything we've talked about so far tonight feeds into a question that we talk about many times in the course, and you might find it as a great way to tie in quantitative reasoning and calculations to bigger pictures, is that every energy choice we make has implications for contributions to atmospheric CO2. So I didn't mention them today. We were working on calculations, but as I know all of you, or certainly almost everybody, was thinking, oh, but using coal has different CO2 implications than using natural gas, and that's absolutely true. How much CO2 is emitted per joule of each fuel is a really important topic to bring up as well. So I want to stop because it's about 6:45 and on the East Coast, and I want to have 5 or 10 minutes to show you about our third edition. So Tommy, this might be a good place to see if anybody else has questions about anything, or if we should move on to talk about my next slide, which is goals of our book and introducing and talking about the third edition.
A couple things did come in. Actually, 2 statements came in, so not questions. I will let, while I'm announcing the statements, I will let some folks again chat in some questions if you have them. Again, just enter the question in chat and choose send questions to staff and I will see it. But Billy actually let us know in reference to the slides that you just went over that NEI.org has some great electricity sources by state, and also New York Times publishes lots of neat diagrams and is another great source of this type of information. So he just wanted to announce that. So thank you, Billy.
Excellent. So is the first one N as in Nancy, NEI?
Yes, so it looks like NancyEmilyIsland.org, NEI.org. So
excellent. Thanks for that. I don't know that one, but now that you mention it, yeah, I believe the New York Times has those graphs that you can hover over different states or different regions of the country, and you get a pie diagram for each. So that's a great suggestion, and thanks for the tip.
Looks like it was the Nuclear Energy Institute. That's it. That's
okay. Excellent.
But yeah, no other questions have come in, but everyone is being attentive. I can tell they're listening and watching. So I think we can kind of jump into the next part.
Okay. So in writing our book, and as we revise it for each new edition, our goals are to provide. Did you say something?
Yeah, I just had one question come in, and this might be leading into what you're about to get into. So sorry for breaking up the breaking off there. Edmund asked, as a first-year APES teacher, he was just curious how significant figures are being viewed on FRQ questions now that calculators are allowed by students.
Wow, that's a great question. So first of all, I should apologize. I realize there are some numbers, and I didn't get any data on our attendees, but right, some of you are just teaching this course for the first time this fall. So I should have said something about adapting to whatever it was you were teaching before, or maybe you're a brand new teacher. But yes, there's a certain aspect that we've done other webinars on. How do you know what's in environmental science and in the AP Environmental Science course, and what's testable? And I think that's a great question now that calculators are allowed, but I want to be really careful. I don't want to misspeak. So I'm going to have to do some research and maybe ask a few people who maybe I can ask the College Board, and maybe we can send an email to people later on. But I honestly don't know how significant figures are going to be used now that calculators are allowed. That is an excellent question, and I don't have an answer off the top of my head, and I certainly don't want to end up misleading anybody. So I'm going to have to use that. Sorry, it's not like an out, but I'm going to have to get back to you.
No worries, and I can look into that as well. So Edmund, we will get back to you about that question.
But that is a great question. Thank you for asking it. Don't you agree, Tommy, that maybe we could send an email to every person who's an attendee and signed up to sort of tell them something about that in a week or two?
Absolutely. We can get that information posted out for sure through the various channels. So we will look.
And you know what else? I bet there's somebody participating who used to be a chemistry APES teacher or currently is doing both APES and chemistry, and they might have a good answer for, I imagine the answer that was, is used in like math or APES would be, math or chemistry would be used in APES, but I don't know that for sure. So we will get back to you. Thank you for that excellent question.
Yes, thank you. So, and leading into what you're about to talk to now, there is lots of great things in your textbook, which I think will be also very useful for a first-year APES teacher. So I'll let you get back to it.
Okay, great. So what we always have wanted to do is provide up-to-date breadth as well as depth, so understanding the scope of what is AP Environmental Science, but then offering depth on particular aspects of it. We don't have a love of doing math just for the sake of doing math, but we use quantitative reasoning when it's needed, and that's very much the philosophy of the AP Environmental Science exam. It's no coincidence I helped create the course curriculum and the early exams, and I had that same philosophy in writing a textbook. We try to use relevant examples whenever possible, and we try to be as unpoliticized, as neutral as we can, not chemically neutral, but politically neutral as possible. So our result, in case there are people, I meet people who are still using the first edition of our book, which was published in 2012. We came out with the butterfly cover in 2015. That was the second edition. And then just earlier this year, we released what we're really excited about, the third edition. And the third edition is 100% aligned with the new 2019 AP curriculum framework and the new AP exam. So I want to make that point, that it came out in January, just a few months after the details were announced, but we really scrambled to make the book totally consistent with the new curriculum framework and the new exam that will be given in May of 2020. So some features about the new edition, the third edition, is that there are AP exam tips scattered throughout each chapter. There's practice math and graphing features, which are, I think, really wonderful and are further examples of the title of this talk and talking about the importance of numerical understanding. So I'll show you that in another slide. There's math review on the back end sheets of the book, and there are two comprehensive tests at the end of the book. So these are two new, similar to 2020 AP exams in environmental science, similar to the format that will be given to your students in May of 2020. And we have two full exams at the back of the book that we wrote. Here's what I want to show you about practice math and graphing. Your students get a chance to analyze, interpret, and generate visual data. So we have things like, photos and illustrations and tables and graphs like we did in the second edition, but we have practice math and graphing at the end of each chapter. And that's what this blue arrow is showing you here, where we say, graph the U.S. population over time with millions of people on the y-axis and year on the x-axis, where we ask your students to take some data in a table and graph it. And that's a great example of something that might show up on an FRQ, or maybe they'd be asked to generate their own data and then graph them. But we now have this exercise at the end of every chapter. So we're really excited about that, and that's something that's new to the third edition. We also have a lot more do the math. So we now have between 1 and 3 do the math boxes in each chapter. We used to have 1 or 2 in most chapters, but now we have them in all chapters. So again, this bullet is repeating what we've said. Scientific calculations, numerical analysis are what some people say is the difference between a student getting a 4 and a 5 on the exam. You can know all the concepts, you can memorize all the facts that might be asked on on multiple choice questions, but unless you can do manipulation of numbers, you might have a hard time getting a 5. So we're really excited about that, with more do the math boxes, and every single one of them has a your turn where we don't give the answer and you can assign that as homework. You have the answer in the teacher's edition, but your students do not. We have modules, which we had in the second edition. We have case studies, which we're excited about. Some of those are new, some of those are updated, some of those are modified, but we have features that we've had previously: the module structure, chapter opening case studies, learning goals, and a running glossary. This is what the modular approach looks like. The butterfly clues you into the fact that this is actually from the second edition, but we have modules in the third edition as well. And we have things like exam prep at the end of every module, and then we have more exam prep kinds of multiple choice and free response questions at the end of the chapters. But even at the end of each module, we changed it, so now it's 4 choices per question, not 5, because that's one of the changes on the exam. We have lots of preparation, as I mentioned, end of chapter. I didn't mention at the end of each unit, we have practice exams just on that unit, content from just that unit. And then, as I already mentioned, we have 2 exams at the end that are cumulative for the whole course. And also, we've had this in both earlier editions. We try to find a good news story, because there is lots of good news, even though there are reasons to be concerned, that there are individuals and organizations making a difference on topics that were covered in a given chapter. So we have working towards sustainability, a feature at the end of every chapter. And perhaps most exciting is we have an updated 3rd edition, Teacher's Edition, written by 2 really talented people who teach environmental science APES, Libby Jones and Alyssa McCracken. And this has all kinds of really good things, including pacing guide and charts of relevant free response questions from past AP exams. But I really like the teaching suggestions, that they actually say, this is what we do in our class when we teach this subject. So I'm a big fan of that. There's other things that you might know about from the previous teacher's editions, if you've seen those, but bell ringers and the teaching tips, as I mentioned, and more practice math, additional math problems that are connected to do the math boxes. But oftentimes we say that if your students are just every week seeing math problems, when they get to their exam at the end of the year, they're not going to have a problem. There are other things I don't have time to go over, but maybe you could look through some of these things. We have a flash drive that has all kinds of teachers' resources, including additional handouts, lab activities, answer keys for the things that there aren't answers in the student edition of the book. And there's Exam View with 1,500 practice multiple choice questions. We have a new thing, Sapling Plus, that I don't know a lot about, but Tommy can help you with that, and ebook access to all those sorts of things. So when I look at, and we ask people, and we put together answers on, what is it about our book that you like so much? And they come up with answers like this. They can tell that it was built from the ground up for AP Environmental Science. It has a modern synthetic approach. It integrates global change and sustainability. As we've talked about, it uses quantitative reasoning. It has relevant examples. And more recently, nobody's had a chance to say this one, but I threw this in. It's fully up to date and aligned with the new curriculum framework and the new AP exam. So I think you get the idea. Here it is again. There are many additional do the math exercises. There's newly added end of chapter math and graphing exercises, and it's completely updated to be consistent with the new exam format. I want to point out that I made some videos for an online course that are available on YouTube and cover many of the chapters in our book and many of the chapters. And some people have told me the students have liked using these as review videos to watch at the end of the year before the exam. So there's the link if you want to look at those. So I appreciate your participating in this. I appreciate your questions. I want to say thank you. We have a few minutes. I'm going to turn it back over to Tommy, but I do want to point out that this is not some robot, or this is my email address. And if there's something that I can help you with in terms of content or things I went over today, I would love to hear from you. If it's more about books and teachers editions, I may not be able to help you, but and you're probably better off going to the other email on the page, and Tommy and his staff will field that. But I thank you very much for participating, and I look forward to whatever questions you might have right now.
Well, so far, no questions coming in, but a couple of thank yous and folks saying the webinar was helpful and useful. So again, I would just like to reiterate, feel free to reach out to Andy for any questions you might have about the content here. But again, definitely make note of that hsmarketing@bfwpub.com email. You can always reach out to that email, whether tonight or tomorrow or 6 months from now, if you have any questions about this book or anything else pertaining to what we offer. We can always put you in touch with your rep or help answer any questions. Also, everyone hang tight about, if you give us a couple days, you will be sent a follow-up email that will include the recording of this webinar, so you can watch it again, as well as Andy's slide deck here, so you can review that as well. But yeah, so far no other questions coming in, just folks saying, I'm up, a couple questions just coming in, which we can answer real quick. So Jennifer asked, do you have suggestions on how to begin introducing math to APE students? How can I make math exciting?
Yeah, so that's a great question, and I know that's a challenge. For one, let's admit for all of us, as I was working through these Tesla calculations today on the battery and kilowatt hours per mile, it generates perhaps anxiety in lots of us, maybe not every single one of us, but it is kind of put some pressure. So absolutely you want to figure out a way to make it fun, or tiny bit fun for your students. So I try to, and again, it depends on what region of the country you're in and what's in the news, but I try to find something that will get an interest in some people. So for some people, it might be the caloric content of the food they eat. If they're athletes and they know they're eating 3,000 or 4,000 kilocalories per day compared to the average person consuming 2,000 or 2,200, maybe that's an angle. Or if they're a car geek, maybe something about fuel efficiency or electric cars. If you are a computer geek, there are some new studies coming out about how much energy, how much electricity is used when you do a typical search engine search. So I heard something, and I haven't tracked this down yet, that you might use the equivalent of 60 watts of some server for perhaps 15 seconds for it to crank up and cool down, and the cooling that goes along with it, for asking a simple question, on Google or some other search engine. So, but that's hard. Send me some ideas that you have, and I'll give you my feedback on them. Or, you tell me about your students, and I'll be able to tell you what are some exciting calculations we can do. But you know your students, and so figuring out what gets them excited is what you got to do, and show them the power of being able to make a calculation and not just have a knee-jerk reaction, oh, this must be good for the environment and this must be bad for the environment, but rather show in terms of energy and perhaps the amount of pollutants or CO2 that are generated. A calculation can really get you much closer to an answer than just like an opinion or a knee-jerk reaction that isn't based on calculations and factual data.
Great. So I know we're over by 1 minute, but there's one last question, Andy. I think if you'd like to answer it, and then we can kind of end the webinar from there.
Absolutely.
So Jeff has asked if there is a resource like the timely Molnar investigations published that you can recommend. So I guess any kind of timely published resources on the top of your mind that you can recommend.
So about specific case studies, or I didn't entirely hear that question.
Jeff, if you want to, he's called it the Molnar, M-O-L-N-A-R. I'm not sure what that is, but Jeff, if you want to email that question.
Oh, maybe that's the lab book, the lab handbook. I'm not 100% sure. No, I'm sorry. So maybe we better do that one offline, just to.
Perfect.
Yeah.
A bunch of folks saying thank you. So I would also like to wrap things up and just say thank you, Andy, for your time and giving this presentation. It really was helpful and useful. And I'd like to thank everyone who attended for their time as well. It means a lot that you all joined and sat here and listened and were with us. So we do appreciate it. And I think I'm going to hit this X here, and it kind of just closes everything out. So if it ends abruptly, let me just say thank you, and stay tuned for that follow-up email. Thank you, everyone.
Thank you. Goodbye, everybody. Take care.